Now let's discuss about this example. I call it a simple artificial neural network. I think this slide is not in the first slide note, so it's a second slide note. Hope you can open the second slide note. It's related to second slide note. Okay. In this example, I will explain the flow or the mechanism of backpropagation in which is represent the training algorithm for artificial neural network. Okay, so why we just discuss the artificial neural network mechanism, the backpropagation mechanism through this simple artificial neural network. So why I call it a simple, because you can see that what is this one? What type of neural network is this one? Is it a single layer perceptron or a multiple layer perceptron? Okay, this is actually a multiple layer perceptron. Because why we call it a multiple layer perceptron? Because you can see that we have, okay, again we have more than two layers. I'm sorry, more than one layer. Means that you have the this is one layer. Okay, this is one layer, which is called output layer, and this is another layer. It's an intermediate between your input layer and output layer. So means that since you have two more than one layer, it's called a multiple layer perceptron. Of course, like I said in the previous lecture, this one is not count, because normally this is not this layer does not have any neuron itself. Okay, this layer do not have any neurons. Okay, even I draw it circle, I don't draw square, because the previous one I draw it as a square. But in this example, I use circle, but you need to just remember the input layer should not have any neuron, means that this X will direct go into this one as a X1, and this one as well as a X1. So means that this arrow will have a signal of X2, this signal also have the signal of X2 going into that direction and that direction. So there's no neuron in this one. There's a purpose I draw it same as there's a purpose I draw this one as a circle same as this one, because later you will see that I need to use the square for other purpose. So just remember that even this artificial neural network is a simple artificial neural network, but it's a multi-layer perceptron, because you have more than one layer. Means that you have a hidden layer and output layer, which consists of neurons there. When I said this consists of neurons, meaning that for each neurons there, you need to have, remember, you will have this one is your input function. Okay, input function, and then this one you have another function is called as a activation function. So each and every neuron will have both function, but in input layer you don't have that one. Means that the process is direct. Just if you X is here, if we flow through this point and going towards this arrow, this line and this line, or this arrow and this arrow. So there's no input function and output activation function, because that is not a neuron, or that is not the node. So okay, so I just label each neuron there, each node there with number there. You have 1, 2, 3, 4, 5, 6, and then this is the input X1 and X2, and then once you compute this one, you will find the Y1 head and Y2 head, which represent the predicted outputs there. Of course, during the training you have X1, X2, Y1 and Y2. There's another question I would like to ask you. What is if this is a classifier, how many classes that this simple artificial neural network can represent? How many classes, how many output classes that this artificial neural network can provide? Of course, it should be 2 classes. Why? That is because you have 2 output here. Remember that we are using the output as a one hot format there. One hot format. So means that you should have the y1, y2. So if the sample here, this, let's say this is your x, okay, if this given this sample, if this sample is class 1, it should be 1 0 here. Okay, if you have the one sample given this sample x, and actually the output should be class 2, then it should be 0 1 here. So means that you only have 2 classes there. Class 1, which is y1 equal to 1, y2 equal to 0, and class 2 where the rest equal to 0, only y2 equal to 1. So it's a one hot encoding formats there. So it's a 2 classes output given two attribute, which is x1 and x2. Okay, then why I label it the nodes in this number? You can see that 1 2 3 4 5 6. So now I can label the w for each arrow there. So this w is w13, means that this w come from this node 1 into this 3. Then you have w23, where it's come from 2 to 3, and then you have w14, which come from 1 to 4. So w24, and then w35, and so on. And then you can see that this I also, in my example, this I don't neglected the bias, the b there. So the b is exists, so that's why there's a b there. So b3 is a bias from the node 3, b5 is the node bias from the node 5, and again we don't have a bias in node 1 and 2 because this is not neuron. Okay, just remember this is not neuron, so that's why we don't have bias there, because remember that the if this is not neuron, then you don't have any input function and activation function. This variable b4, w14 and 24 will be used at the input function. So that's why anything which is not neuron should not have the bias. So that is the reason. Okay, so that's how I label. Then of course from here you can express this the error there, or the cost function for each and every output there. Once you're given the x, you do the when you compute all this one, this is what we call a forward pass. Okay, forward pass, going into that direction, forward pass, and then you find the y, and then you have the y head, and then you know the actual y1, and then this is the expression represent the errors there. Remember, this is again I'm using the SSE as a cost function or as an error there. Let's say you want to change this one, you don't want to use SSE, you want to use MSE. So the expression will look like this: E1 equal to 1 over 2 to the power of n summation I, and then you need to have y y1i minus y1i. So this is MSE. Okay, but in my example, because we want to talk about this, the bigger picture of this mechanism, I just do the scope. Assume that I using SSE to develop my cost function. Okay, I'm not using the the MSE. So this is the MSE, meaning that to find the error of MSE, you need to test on a bunch of data set, a bunch of data from your training data set, because this I will be vary according to how many sample in your data set. Let's say your data set have 100, so this n equal to 100. You need to compute 100 times before you can compute your E1. But SSE, we don't have to compute 100. You just take one sample of data, means that sample number 1 you compute, then you already can get your E1. But if you talk about MSE, in order for you to obtain the E1 here, you need to compute all fully 100 sample inside your data set or inside your training data, then you can compute the E1. So that is the difference. Okay, but here I'm using SSE. So what is the different definition of cost function as between the linear method and artificial neural network? You can see that, okay, if you talk about the linear method for classification of regression, the cost function here, E, you are directly defined as your J theta. Okay, remember your J theta is this expression. I think in the previous class we discuss about this one. If you talk about using MSE, okay, this one. But however, for artificial neural network, you cannot define your cost function as only the E1, because in artificial neural network you have several output. In this case, you only have, in my simple artificial neural network, you only have two output, okay, Y1 and Y2. But later when you want to design your own artificial neural network, for sure if you talk about 3 classes, you will have a 3 output. If you want to design a 4 classes, you will have a 4 output. So meaning that for artificial neural network, the cost function is not this one, okay, it should be this one. It's a total error. This should be your J theta in artificial neural networks, meaning that let's say later if you using the MSE, you don't want to use SSE, you're using MSE. So at this point you get one MSE that is represent your E1, and then you apply the MSE here, you will provide or you produce the E2. So you have 2 errors there, but or 2 cost function there. So because you have 2 cost function, that's why this is not called as the whole cost function. Okay, it's just a cost function for that particular output Y1. Okay, this one is only cost function for this particular output Y2. But to represent the cost function of whole network, then you need to total it like this. So that's why I said that now the cost function for neural network is not only this one, so you need to total up. So now that is the difference between the cost function in this neural network and the linear method that you learned before, because the one that you learned before, the output is only one output there, only one output. So that's why you can directly use the MSE as your output. But in neural network, because you have multiple output, so that's why you need to calculate each MSE, and for each output there you need to total up. That total up function expression is actually represent the total or the cost function that represent the whole artificial neural model that you design. So just remember that is the different things there. But in my example, I don't use MSE, I use SSE there. So calculate one SSE, I get E1. SSE for Y2, I get E2. So then now my cost function or my total error, I'm using the word error there, or my total error or the error there is equal to E1 plus E2 there. So just remember that. Okay, that is the discussion about this cost function. Now just remember the error is E1 plus E2. Okay, so then remember that for each neuron, when I said neuron is the one that involved is only the point of number 3, 4, 5 and 6. 1, 8 and 2 is not involved because this one is not neuron, or it's not a node. So just again remind you, this is the component. You have an input function and the activation function, and then this one is a linear equation. Actually, input function is a linear equation, the same linear equation. So then if I express there, again I'm using the notation now node. Okay, just remember I already told you that previously we used V here, but now I'm not using V because it's not meaningful. So that's why I'm using a net there. Okay, just change the variable name, so you don't have to worry about that, because net here is more meaningful, because net actually represent this network. So net is equal to W1 I1 plus W2 I2 plus bias time 1. So that is where this expression come from. And then to find the O there, the output of this network, or this neuron, I use the word O there. O means the output of this neuron. So to find the output for this neuron is equal to your activation function F, where the input is the net. Okay, so back to this picture again. At the hidden layer, remember this is the input layer, this is the hidden layer. So now you can express one by one. You need to express to find the net and the O there for each and every node there. For node 3 or neuron 3, net 3, you just define that net 3 is equal to W12 multiply with your X. Okay, just remember that this should be X1, this one is also X1. Okay, going into that direction and that direction. This is your X2 going into that direction, X2 going to that direction. So this line, there's a X1 signal, then you need to multiply it with this one, and then this X2 going to that direction, multiply with this W23 plus a bias time 1, that is a net 3 there, this expression. Then you the O3, which is the output at this neuron 3, this is O3. Okay, going into that direction and that direction, and this is your O4 going into that direction and going into towards that direction. So it equal to your activation function. So here I don't set my activation function yet. What type of activation function I'm use for each and every neuron there. I just put F there. Later we can manipulate that just by, if you set it into sigmoid function, it become like this. If you set into, let's say, tan function, then it's another way around there. Okay, so just put F there because it is still our activation function. So to find the O3 or O4, you need to execute your activation function at this neuron with the input of which is the input is net 3, where the net 3 is come from the linear equations there. So this one is for neuron 3, this one is for neuron 4. So what happened to the output layer? It is similar things there happens. So to find the net 3, when you find this example, just remember the setup there. It should be this is a net, this is F, this is net, this is F. Okay, F net. So net is or we can use also summation, because net is the variables. Sorry. So it's the same thing happen. Means that you have two expression, you have two function there. This one is a input function, this one is activation function. So to find net 5 is a W35 multiply with O3. Okay, remember this is still O3 there. This is O4. So that's why you develop this one. So you can see that first we compute, okay, first we compute this stage, and then we the hidden layer expression, then we compute the output layer expression. So you can see that it's going into that direction, the process. So that's why they call it a forward pass. Okay, once you have this one, you have this one, just remember this one is already given, because this is come from your training data. Of course, this is your training data, you know the value, and this value is actually initially when you want to run the algorithm, it will initialize by using random number. You just put a random number at this one for the first time iteration. So that's why you also know the value for each and every W and B inside the network. So once you know the X and the W, you know how to compute your O3, net 3, O3, net 4, O4, and then from this value going into that direction, because you know already your W and B, then you know how to compute your O. Here it should be O5 and O6, and again once it's arrived at the output there, it should be, of course, the Y. O5 is actually your Y head 1. Okay, Y head 1. This one is equal to your Y head 2. So it's the same things there. Okay. So that's the name is forward pass, because you're going into from the input to the output. So that's why it's a forward pass. Then if I summarize the forward pass, that is the equations there happen at the hidden layer. This is what you do compute. Once you know this one, then based on this result, you will use the result to compute this one, because this O3 is here, O4 here. So O3 and 4 need to be known when you compute the hidden layer, because at the hidden layer you want to know what is the value of O3 and O4. Once you know the O3 and O4, you put here, then you know what is your O5 and O6, which is similar to your Y1 hit and Y2 hits there. Okay, that is forward pass. Now